Hey, this is Sleeper. Welcome back to my channel. We are continuing the bug bounty job role path with the file inclusion module. Just an FYI, this is the last tier 0 module, meaning I can walk through this completely with the exercises and skills assessment, but here on out, any further modules, I'll only be able to read the material. Just an FYI. If you need access to Hack the Box Academy, I definitely recommend the Silver Annual Plan, as it gives you access to all modules up to and including Tier 2 and all 3 job role paths. It includes 1 exam voucher per year, which is good for 2 exam attempts. So let's go ahead and get started. Intro to file inclusions. Many modern back-end languages, such as PHP, JavaScript, or Java, use HTTP parameters to specify what is shown on the web page, which allows for building dynamic web pages, reduces the script's overall size, and simplifies the code. In such cases, parameters are used to specify which resource is shown on the page. If such functionalities are not securely coded, an attacker may manipulate these parameters to display the content of any local file on the hosting server, leading to a local file inclusion (LFI) vulnerability. Local file inclusion (LFI). The most common place we usually find LFI within is templating engines. In order to have most of the web application looking the same when navigating between pages, a templating engine displays a page that shows the common static parts, such as the header, navigation bar, and footer, and then dynamically loads other content that changes between pages. Otherwise, every page on the server would need to be modified when changes are made to any of the static parts. This is why we often see a parameter like index.php page equals about, where index.php sets static content, for example the header or footer, and then only pulls the dynamic content specified in the parameter, which in this case may be read from a file called about.php. As we have control over the about portion of the request, it may be possible to have the web application grab other files and display them on the page. LFI vulnerabilities can lead to source code disclosure, sensitive data exposure, and even remote code execution under certain conditions. Leaking source code may allow attackers to test the code for other vulnerabilities, which may reveal previously unknown vulnerabilities. Furthermore, leaking sensitive data may enable attackers to enumerate the remote server for other weaknesses, or even leak credentials and keys that may allow them to access the remote server directly. Under specific conditions, LFI may also allow attackers to execute code on the remote server, which may compromise the entire back-end server and any other servers connected to it. Examples of vulnerable code. Let's look at some examples of code vulnerable to file inclusion to understand how such vulnerabilities occur. As mentioned earlier, file inclusion vulnerabilities can occur in many of the most popular web servers and development frameworks like PHP, Node.js, Java, .NET, and many others. Each of them has a slightly different approach to including local files, but they all share one common thing: loading a file from a specific path. Such a file could be a dynamic header or different content based on the user's specified language. For example, the page may have a language get parameter, and if a user changes the language from a drop-down menu, then the same page would be returned but with a different language parameter. For example, language equals ES. In such cases, changing the language may change the directory the web application is loading the pages from, for example, EN or ES. If we have control over the path being loaded, then we may be able to exploit this vulnerability to read other files and potentially reach remote code execution. PHP. In PHP, we may use the include function to load a local or a remote file as we load a page. If the path passed to the include is taken from a user-controlled parameter, like a get parameter, and the code does not explicitly filter and sanitize the user input, then the code becomes vulnerable to file inclusion. The following code snippet shows an example of that. We see that the language parameter is directly passed to the include function. So any path we pass in the language parameter will be loaded on the page, including any local files on the backend server. This is not exclusive to the include function, as there are many other PHP functions that would lead to the same vulnerability if we had control over the path passed into them. Such functions include once, require once, file gets contents, and several others as well. Note: in this module, we will mostly focus on PHP web applications running on a Linux backend server. However, most techniques and attacks would work on the majority of other frameworks, so our examples would be the same with a web application written in any other language. Node.js. Just as the case with PHP, Node.js web servers may also load content based on an HTTP parameters. The following is a basic example of how a get parameter language is used to control what data is written to a page. As we can see, whatever parameter passed from the URL gets used by the read file function, which then writes the file content in the HTTP response. Another example is the render function in the express.js framework. The following example uses the language parameter to determine which directory it should pull the about.html page from. Unlike our earlier examples where get parameters were specified after a question mark character in the URL, the above example takes the parameter from the URL path, for example, about n or about es. As the parameter is directly used within the render function to specify the rendered file, we can change the URL to show a different file instead. Java. The same concept applies to many other web servers. The following examples show how web applications for a Java web server may include local files based on the specific parameter, including using the include function. The include function may take a file or a page URL as its argument and then renders the object into the front-end template, similar to the ones we saw earlier with Node.js. The import function may also be used to render a local file or a URL, such as the following example. .NET. Finally, let's take an example of how file inclusion vulnerabilities may occur in .NET web applications. The response.write file function works very similarly to all of our earlier examples, as it takes a file path for its input and writes its content to the response. The path may be retrieved from a get parameter for dynamic content loading as follows. Furthermore, the @html.partial function may also be used to render the specified file as part of the front-end template, similarly to what we saw earlier. Finally, the include function may be used to render local files or remote URLs, and may also execute the specified files as well. Read versus execute. From all the above examples, we can see that file inclusion vulnerabilities may occur in any web server and any development frameworks, as all of them provide functionalities for loading dynamic content and handling front-end templates. The most important thing to keep in mind is that some of the above functions only read the content of the specified files, while others also execute the specified files. Furthermore, some of them allow specifying remote URLs, while others only work with files local to the backend server. The following table shows which functions may execute files and which only read file content. So this looks like a great reference here. This is a significant difference to note, as executing files may allow us to execute functions and eventually lead to code execution, while only reading the file's contents would only let us to read the source code without code execution. Furthermore, if we had access to the source code in a white box exercise or in a code audit, knowing these actions helps us in identifying potential file inclusion vulnerabilities, especially if they had user-controlled input going into them. In all cases, file inclusion vulnerabilities are critical and may eventually lead to compromising the entire backend server. Even if we were only able to read the web application source code, it may still allow us to compromise the web application, as it may reveal other vulnerabilities as mentioned earlier, and the source code may also contain database keys, admin credentials, or other sensitive information. Local file inclusion. Now that we understand what file inclusion vulnerabilities are and how they occur, we can start learning about how we can exploit these vulnerabilities in different scenarios to be able to read the content of local files on the backend server. So basic LFI. The exercise we have at the end of this section shows us an example of a web app that allows users to set their language to either English or Spanish. If we select a language by clicking on it, for example Spanish, we see that the content text changes to Spanish. We also notice that the URL includes a language parameter that is now set to the language we selected, for example PHP, or we selected Espanol.php. There are several ways the content could be changed to match the language we specified. It may be pulling the content from a different database table based on the specified parameter, or it may be loading an entirely different version of the web app. However, as previously discussed, loading part of the page using template engines is the easiest and most common method utilized. So if the web application is indeed pulling a file that is now being included in the page, we may be able to change the file being pulled to read the content of a different local file. Two common readable files that are available on most backend servers are etc password on Linux and windowsboot.ini on Windows. So let's change the parameter to etc password from ES. As we can see, the page is indeed vulnerable, and we are able to read the content of the password file and identify what users exist on the backend. Path traversal. In the earlier example, we read a file by specifying its absolute path, For example, Etsy password. This would work if the whole input was used within the include function without any additions, like the following example. In this case, if we try to read Etsy password, then the include function would fetch that file directly. However, in many occasions, web developers may append or prepend a string to the language parameter. For example, the language parameter may be used for the file name and may be added after a directory as follows. In this case, if we attempt to read Etsy password, then the path passed to the include function would be \languages \Etsy password. And as that file does not exist, we will not be able to read anything. As expected, the verbose error returned shows us the string passed to the include function, stating that there is no Etsy password in the languages directory. Note, we are only enabling PHP errors on this web application for educational purposes, so we can properly understand how the web application is handling our input. For production web applications, such errors should never be shown. Furthermore, all of our attacks should be possible without errors, as they do not rely on them. So we can easily bypass this restriction by traversing directories using relative paths. To do so, we can add .. before our, is that backslash or forward slash? Before our file name, which refers to the parent directory. For example, if the full path of the languages directory is var /HTML languages, then using .. /index.php would refer to the index.php file on the parent directory, which was var /HTML index.php. So we can use this trick to go back several directories until we reach the root path, and then specify our absolute file path. For example, .. /back .. // Etsy password, and the file should exist. So as we can see, this time we were able to read the file regardless of the directory we were in. This trick would even work in the entire parameter. This trick would even work if the entire parameter was used in the include function. So we can default to this technique, and it should work in both cases. Pardon me. Furthermore, if we were at the root path and used .. then we would still remain in the root path. So if we were not sure of the directory the web application is in, we can add .. many times, and it should not break the path, even if we do it 100 times. Tip: it can always be useful to be efficient and not add unnecessary .. several times, especially if we were writing a report or writing an exploit. So always try to find the minimum number of .. slashes that work and use it. You may also be able to calculate how many directories you are away from the root path and use that many. For example, with var /HTML, we are 3 directories away from the root path, so we can use it 3 times. File name prefix. In our previous example, we used the language parameter after the directory, so we can traverse the path to read the password file. On some occasions, our input may be appended after a different string. For example, it may be used with a prefix to get the full file name, like the following example. In this case, if we try to traverse the directory with .. Etsy password, the final string would be lang _ .. Etsy password which is invalid. And as expected, the error tells us that this file does not exist. So, instead of directly using path traversal, we can prefix a slash before our payload. And this should consider the prefix as a directory. And then we should bypass the file name and be able to traverse directories. Note, this may not always work, as in this example, a directory named lang_slash may not exist, so our relative path may not be correct. Furthermore, any prefix appended to our input may break some file inclusion techniques we will discuss in upcoming sections, like using PHP wrappers or wrappers and filters, or RFI. Appending extensions. Another very common example is when an extension is appended to the language parameter as follows. This is quite common, as in this case, we would not have to write the extension every time we need to change language. This may also be safer, as it may restrict us to only include PHP files. In this case, if we try to read etc password, then the file included would be etcpassword.php, which does not exist. There are several techniques that we can use to bypass this, and we will discuss them in upcoming sections. Exercise. Try to read any PHP file, for example, index.php, through LFI, and see whether you would get its source code or if the file gets rendered as HTML instead. Second order attacks. As we can see, LFI attacks come in different shapes. Another common and a little bit more advanced LFI attack is a second order attack. This occurs because many web application functionalities may be insecurely pulling files from the backend server based on user-controlled parameters. For example, a web application may allow us to download our avatar through a URL like profile $username avatar.ping. If we craft a malicious LFI username, for example, ////etc_password, then it may be possible to change the file being pulled to another local file on the server and grab it instead of our avatar. In this case, we would be poisoning a database entry with a malicious LFI payload in our username. Then another web application functionality would utilize this poisoned entry to perform our attack. For example, download our avatar based on username value. This is why this attack is called a second order attack. Developers often overlook these vulnerabilities as they may protect against direct user input, for example from a $page parameter, but they may trust values pulled from their database, like our username in this case. If we manage to poison our username during our registration, then the attack would be possible. Exploiting LFI vulnerabilities using second-order attacks is similar to what we have discussed in this section. The only variance is that we need to spot a function that pulls a file based on a value we indirectly control and then try to control that value to exploit the vulnerability. Note: all techniques mentioned in this section should work with any LFI vulnerability, regardless of the back-end development language or framework. So we've got a couple questions. We'll spawn our target. Using the file inclusion, find the name of a user on the system that starts with B. And the number 2 question, submit the contents of the flag.txt file located in the user share flags directory. So we'll grab our IP address and head to our bone box and load this in our browser. Okay, so we have English and Spanish. We'll go to Spanish. And then it wants us to see if we have local file inclusion vulnerability. We'll just try etc password at first. And nothing comes up. So we'll try it with the dot slashes. At least 3 of them. And try it again. And there we go. So we're looking for a user that starts with B, and I see Barry. Lagging a little bit. So we'll input that. Body. Great show. And then the second question, submit the contents of flag.txt located in user, share, flags, flag.txt. So we'll just use that, user share flags, in the same fashion. User share flags, and then flag.txt. There we go. Never trust user input. Basic bypasses. In the previous section, we saw several types of attacks. Pardon me. In the previous section, we saw several types of attacks that we can use for different types of LFI vulnerabilities. In many cases, we may be facing a web application that applies various protections against file inclusion, so our normal LFI payloads would not work. Still, unless the web application is properly secured against malicious LFI user input, we may be able to bypass the protections in place and reach file inclusion. Non-recursive path traversal filters. One of the most basic filters against LFI is a search and replace filter, where it simply deletes substrings of ... to avoid path traversals. For example, so it's string replace ... with a blank space. So the above code is supposed to prevent path traversal and hence renders LFI useless. If we try the LFI payloads we tried in the previous section, we get the following error. We see that all ... substrings were removed, which resulted in a final path being languages/etc password. However, this filter is very insecure as it is not recursively removing the ... substring, as it runs a single time on the input string and does not apply the filter on the output string. For example, if we use 4 dots and 2 slashes as our payload, then the filter would remove just that single ... and the output would be ... which means we may still perform path traversal. Let's try applying this logic to include etc password again. So you double it up, it'll take it out, but it still works. As we can see, the inclusion was successful this time, and we're able to read etc password successfully. The 4 dots and 2 slashes substring is not the only bypass we can use, as we may use ... or 4 dots / /. and several other recursive LFI payloads. Furthermore, in some cases, escaping the / character may also work to avoid path traversal filters. For example, the forward dots, / and backslash. Or adding extra /, 4 dots and 4 /. Encoding. Some web filters may prevent input filters that include certain LFI-related characters, like a dot or a slash, used for path traversals. However, some of these filters may be bypassed by URL encoding our input, such that it would no longer include these bad characters, but would still be decoded back to our path traversal string once it reaches the vulnerable function. Core PHP filters on versions 5.3.4 and earlier were specifically vulnerable to this bypass, but even on newer versions, we may find custom filters that may be bypassed through URL encoding. If the target web applications did not allow dot and backslash in our input, we can URL encode / into that, which may bypass the filter. To do so, we can use any online URL encoder utility or use the Burp Suite decoder tool as follows. Note: for this to work, we must URL encode all characters, including the dots. Some URL encoders may not decode dots as they are considered to be part of the URL scheme. Let's try to use this encoded LFI payload against our earlier vulnerable web application that filters the .. strings. As we can see, we were able to successfully bypass the filter and use path traversal to read etc password. Furthermore, we may also use burp decoder to encode the encoded string once again to have a double encoded string, which may also bypass other types of filters. You may refer to the command injections module for more about bypassing various blacklisted characters, as the same techniques may be used with LFI as well. Approved paths. Some web applications may also use regular expressions to ensure that the file being included is under a specific path. For example, the web application we have been dealing with may only accept paths that are under the /languages directory as follows. To find the approved path, we can examine the request sent by the existing forms and see what path they use for the normal web functionality. Furthermore, we can fuzz web directories under the same path and try different ones until we get a match. To bypass this, we may use path traversal and start our payload with the approved path, and then use / to go back to the root directory and read the file we specify as follows. Some web applications may apply this filter along with one of the earlier filters, so we may need to combine both techniques by starting our payload with the approved path and then URL encode our payload, or use recursive payload. Note: all techniques mentioned so far should work with any vulnerability, LFI vulnerability, regardless of the back-end web development language or framework. So .languages was our approved path, and then we're able to LFI after that. Appended extension. As discussed in the previous section, some web applications append an extension to our input string, for example, .php, to ensure that the file we include is in the expected extension. With modern versions of PHP, we may not be able to bypass this and will be restricted to only reading files in that extension, which may still be useful, as we will see in the next section. For example, reading source code. There are a couple of other techniques we may use, but they are obsolete with modern versions of PHP and only work with PHP versions before 5.3 or 5.4. However, it may still be beneficial to mention them, as some web applications may still be running on older servers, and these techniques may be the only bypasses possible. Path truncation. In earlier versions of PHP, defined strings have a maximum length of 4096 characters, likely due to the limitation of 32-bit systems. If a longer string is passed, it will simply be truncated, and any characters after the maximum length will be ignored. Furthermore, PHP also used to remove trailing slashes and single dots in path names. So if we call etc password /dot, then the /dot would be truncated, and PHP would call etc password. PHP and Linux systems in general also disregard multiple slashes in the path. / etc password is the same as etc password. Similarly, a current directory shortcut dot in the middle of the path would be also disregarded, etc.password. If we combine both of these PHP limitations together, we can create very long strings that evaluate to a correct path. Whenever we reach the 4096 character limitation, the appended extension PHP would be truncated, and we would have a path without an appended extension. Finally, it is also important to note that we would also need to start the path with a non-existing directory for this technique to work. An example of such payload would be the following: non-existing directory // etc password, and we repeat that 2048 times approximately. Of course, we don't have to manually type / 2048 times, total of 4096 characters, but we can automate the creation of this string with the following command. We may also increase the count of .. as adding more would still land us in the root directory, as explained in the previous section. However, if we use this method, we should calculate the full length of the string to ensure only PHP gets truncated and not our requested file at the end of the string. This is why it would be easier to use the first method. And null bytes. PHP versions before 5.5 were vulnerable to null byte injection, which means that adding a null byte %00 at the end of the string would terminate the string and not consider anything after that. This is due to how strings are stored in low-level memory, where strings in memory must use a null byte to indicate the end of a string, as seen in assembly, C or C++ languages. To exploit this vulnerability, we can end our payload with a null byte, so etc password with our null byte, such that the final path passed to include would be etc password nullbyte.php. This way, even though PHP is appended to our string, anything after the null byte would be truncated, and so the path used would actually be etc password, leading us to bypass the appended extension. We'll spawn our target. And our question here: the above web application employs more than one filter to avoid LFI exploitation. Try to bypass these filters to read flag.txt. So let's take a look. Okay. So it's calling the languages. So it's calling a good path first. So we'll just try our normal Etsy password and see what happens. Nothing happens. So let's try this. Let's just go and see what we have. So there's multiple filters. We can see which ones we can try. So we're trying approved path. We might need to URL encode this. So our ... is actually going to be %2e, %2e, %2f. F is the slash. So we'll just try that and see what happens. %2e, %2e, %2f. %2e, %2e, %2f. And we'll copy that. And we'll do that 5 times. 1, 2, 3, 4. That was the 5th. And we'll put this here in between Etsy password. And that didn't work either. There's some dots here. So let's just try to encode it then, like it does in Burp. And we'll take a look at the other methods. This is using a dot here. So maybe we need a dot. We can also see if it's this maximum length. Except we're not seeing the extension, so. So we can just do kind of like what it has. So decoder, let's just go ... Etsy password. Encode as URL. So copy all that. And paste this in here. Illegal path. Maybe it's this dot. We'll take a look. Illegal path. Let's see. We're trying to just go to flag, so maybe we can shoot for that. Just flag. Yeah, flag.txt. Go to the end. Illegal path specified. So let's take a look. Maybe the entire thing. So language. Well, actually, this slash wasn't there before. Okay. So let's try it. Let me just copy that first. This is what we had. URL encoded. And let's just try it without the slash. Okay, so it does just want this, right? So now, let's see, var HTML languages. It should be 4, so that should work, right? Flag.txt. And let's just go languages. Let's try to just URL encode the entire thing. Oops, control copy. Let's do it again. Decode as URL. Oops. Encode as URL. Okay, we'll copy this and jump back to, where's our box? I mean our browser. So now this entire thing is URL encoded. Illegal path specified. Okay, so let's look at our other filters. So we had non-recursive. So maybe it's replacing the string. So we can try the fours. Let's try the fours. And was it just one backslash? Let's check. Double. So double. Language is. Let's just verify. Language. Okay. So we'll copy this. And try that. Language slash. Sorry, slashes are becoming that. It's not necessarily taking this out. So let's take a look at our other options. Encoding. So we tried the first method, we tried the second method. We tried the entire payload there. Maybe we do need the dot for the current directory, so we'll try that. So dot slash control all from here. Copy. See if we can just go dot slash language dot slash illegal path specified. So it wants language, right? /en .php. So it might have that PHP at the end. Append extension. So let's try with the null byte, right? That was the last one here. So let's try with the null byte. Percent %oo. Let's get rid of this. Control copy. Languages was part of it. Language. Legal path. This was the double. So let's try just 2 dots. 2 dots with a null byte. And the specified path. No good. So the last thing here is this. So let's use this code. This is asking for a non-existing directory. snip. Oh yeah. Okay. So just this top part. So it might be this and URL encoding, maybe with the null byte. Let's check. So we have the code. Let's run that code. Etsy password. Oh geez. Okay. So we're going to copy that. And non-existing directory. So we're going to copy this and paste this in. How about with language? Languages. Language. And we'll have to add a couple more. So slash dot. Okay. Let's try to copy this. Jump to burp. And then let's just do both just in case. So let's do language. Let's just URL encode. Let's see. How can we do this? We just want the first part. Oh, geez. Okay, so we can just delete that. The first part, we'll add the null byte. No, we'll just URL encode this. So we'll grab the bottom, copy that. So we're just gonna keep everything else, but URL encode this first part. Okay. Let's see what our hint says. Try to see what path the regular functionality uses. Well, the regular functionality uses the language path. The regular functionality uses. It is language. Languages. Oh, it was supposed to be an S. So maybe we just add an S. I've been trying language this whole time. And let's just add a null byte for fun. Nothing. So let's get rid of the null byte. Try it again. Okay. So we'll backtrack. We'll try the double. And then there's two of these, right? So 2F, 2F, 2F. Dot dot. Dot dot. We need it one more time, I think. Dot 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 dot. 2F. So it doesn't cut it out, right? So we're not trying to go to Etsy password. We're trying to go to the flag.txt. So double doesn't work. So let's just try it single again. .2fe. 2f. Dot slash flag.txt. This is the, this looks correct. We're not getting an error, so we're getting closer, right? Let's try a null byte. No good. Okay. \flag.txt. It employs more than one filter. So we tried the null byte, right? That didn't work. Maybe it's this one. So we'll try the code again, but with flag at the end. It says non-existing path, so let's just see if it's a character limit. So we'll run the same thing here, but with just flag.txt. So it said it's important that the directory doesn't exist for this one. So we'll just check. It doesn't like that, so it must be that it uses it. And it doesn't like that either. So it's most likely not one of those two. So it is this, right? It's using the approved path. This is our error. So it's using the approved path, and I bet you it's something simple like the first one. We'll try it. So it's not removing it. We can check. Let's see if it's this one. Try the URL encode. Copy this. We're really trying everything here. Maybe it doesn't need that. Basic bypasses. So we'll try the double again. Try it here. Dot dot slash dot dot slash dot dot slash dot dot slash. No good. So maybe it's not working. Let's try one of these. Triple dot backslash. Okay, we'll try that. Okay. And then finally, 4 dots, / backslash. Like that. / backslash. Yes. Okay. Illegal path specified. So, let's see. The slashes are getting URL encoded. The / is still there. Let's just see real quick. Oops. See what happens here. So we tried them all URL encoded. Now we're going to try them just normally. Just to cover all our bases. With a null byte. And without. Oops. Okay. Okay. There we go. So we had to try everything. It has the, what's it called? The approved path. Where is that? Approved path. We have to include that. And then it said there's another LFI filter, more than one. So the / wouldn't work. We tried the URL encoded version of that, but then going back and trying them manually without URL encoding, the triple / is the one that ended up working. So basic filters won't stop LFI. And submit that there. And here is a great place to stop. We will continue with our file inclusion module next time, starting with PHP filters and moving on to the rest of this module. So once again, my name is Sleeper, and that's a wrap. Until next time.